The next thing we want to talk about are heating curves. So this is an example of a heating curve over here on the left. And you see that on the y-axis is temperature. And in the article we read earlier, it mentions a new unit of temperature, and that is Kelvin. And we'll learn more about Kelvin scale when we get to the gas law unit, but know that Kelvin goes from 0 and up. There are no negative numbers in Kelvin. And so with time, we're measured in minutes, and we can see as time goes on, my substance, whatever this is heating up. My temperature is going upwards, okay? So that means my average kinetic energy is going up, the overall speed of my molecules is speeding up. Now, you can imagine that there is also the reverse, right? So if you look over on the right, I'm just going to draw a picture. So if we have one where instead, if we're looking at time and temperature, okay, sorry for my sloppy handwriting, if you start off at a high temperature and begin to cool down, okay, then this would be referred to as a cooling curve. So you need to be familiar with both. Okay, so what we're going to do is we're going to spend a few minutes going over each part of this graph. Okay, so if we look at point A on the graph, so right here where that green dot is, at point A, the atoms are solid. So you have a solid there. Atoms are vibrating slowly. Okay, we know that solids move the slowest. They have the lowest average kinetic energy, and that is why their temperature is low. And so at this point, energy is going to be used for increasing the average kinetic energy. And if you didn't watch the video before this, I recommend that you do so. But average kinetic energy is going to be abbreviated as AKE from now on. And so as as time goes on, my temperature is going to go up. Okay, so this is kind of what we're looking at. And so for that whole segment there, okay, segment AB, this is just when you still have all solid, okay, there is no liquid present at this point. The atoms are speeding up, okay, and the reason why we know this is because there is an angled portion of the line. So in all cooling curves, and heating curves, there are angled lines or angled segments, and then there are flat segments. And so those segments mean different things. And so with this segment, it's angled, and so that means it's speeding upward, or the molecules are speeding up because the temperature is going up. And so that means energy is being used for average kinetic energy. And this amount of energy we just call heat, and we abbreviate heat as Q. Okay. Now, once we get to point B, we are still 100% solid. Okay, and that's important to note that that whole segment, we have stayed solid every single time. And so the atoms are faster than A, okay, at point B. We're the fastest we've gotten, and the energy is going to be used for something a little bit, well, it's still being used for average kinetic energy at this point. All we've done is we've been speeding up, but when we get to this flat segment here, that is where things start to change. We see this segment and we say, man, that's flat. And so in segment BC, this is when you have melting occur, okay? And so you are going to have solid and liquid present. okay? And so during this phase, we see that the temperature remains constant. And so if the temperature does not change, the atoms are staying the same speed, which is what we talked about in the last question of the previous video. And so that means energy is being used to break intermolecular forces. If we are looking at the cooling curve equivalent, which would be this segment right here, this first green or this last green segment, intermolecular forces would be forming in order to become a solid. Okay, and so this amount of energy is called heat of fusion. Now, heat of fusion is often written as delta H fusion. Okay, and we'll talk about what delta H means, and we'll see this come back up again. But for now, I want you to connect the word fusion with melting and freezing. It requires the same amount of energy to do both. And so at point C, all melting has occurred, and so now I'm 100% liquid. So halfway between B and C, you'd have 50% solid, 50% liquid, but at this point you are 100% liquid. The atoms are the same speed as B still, and the energy is going to be used for average kinetic energy because melting is finished at point C, and so only during melting or only during a phase change are we breaking or forming bonds. So now if we look at segment CD, which is the next angled part, this is where we are 100% liquid still, okay, but now the liquid atoms are speeding up. Okay, we see that the temperature increases. And so that means energy is being used for average kinetic energy because that's what temperature measures. And again, this is just heat. Okay, so Q is the abbreviation for heat. If you want to know why it's Q and not H, look it up, ask Siri, call Google, I don't know, figure it out. And so at point D, we are still all liquid, okay, and the atoms are faster than C, and the energy is still being used for average kinetic energy, okay. Now, once we are at point D, we are starting to get to a flat segment again, and so during this segment, when we're changing from a liquid, we're going to see vaporization occur. Now, under vaporization, you have two kind of categories. You have evaporation and you have boiling, and they are actually different things. And we can talk about what that means if you come see me, but I'm not going to put it in this video because it's a little bit outside of the scope of this course. If you choose to take AP Chemistry, you'll talk about what the difference between those two things are. But in this case, atoms are staying constant, okay, with the speed, and energy is being used for breaking the intermolecular forces, okay? And this amount of energy is called heat of vaporization, which makes sense because that is what is occurring. And so heat of vaporization is often abbreviated as delta H vape for vaporization. And so once we have reached point E, we have time has passed, all vaporization has occurred, then I am 100% gas. The atoms are the same speed still. I don't need to write still in our notes. It's the same speed as point D. And the energy is being used for average kinetic energy again. And we'll see that in this segment because once it switches to being used for average kinetic energy, the atoms in segment EF are still a gas, But the atoms are speeding up. Energy is being used for average kinetic energy. The amount of heat, or the amount of energy, which is a form of heat, well, heat is a form of energy, is Q. And point F is all gas still. The atoms are the fastest they've been, and energy is used for average kinetic energy still. So you can see that most of the time, average kinetic energy is what energy is being used for, and only during a phase change is it being used to break or form bonds. This is not in your notes, but one thing I would like to point out is that if you overlap a heating curve with a cooling curve, and we begin to label things, we know that if you heat, so we're looking at this purple line first, you start off as a solid, you heat up, you begin to melt, so melting occurs, and then you are a liquid, then vaporization occurs, and then you have a gas. Well, with a cooling curve, it is the opposite. You start with a gas, and then the opposite of vaporization is condensation. And then you have a liquid, and then you begin to freeze, which is the opposite of melting, and then you end in a solid. Now, there are a few comparisons I would like to make, and if my drawings are not 100% to scale, then please forgive me because I'm not an artist. But if you'll notice, melting and freezing are happening at the same temperature. And so if this is for water, okay, melting and freezing will always happen at 0 degrees Celsius, okay? And it happens at the same time. The only difference is whether or not you're heating up or cooling down. And the same can be said for condensation and vaporization, okay? Now, vaporization, which is boiling, we know the boiling point of water is 100 degrees Celsius. And so at 100 degrees Celsius, gas can condense to form a liquid, and liquid can vaporize to form a gas. So both options are available. It just depends on whether or not you are adding energy or it is being released. Okay, so that's just a little bit of added information there that I want to make sure is very clear. We'll be asked many questions about what is happening at different points along the curve, and you need to be able to explain that. Check out your warm-ups for some sample multiple choice problems and how to look at the correct answers. Take a look at the next video for the continued notes.